Hey, all the work we've been doing on series has really been to prepare ourselves to study power series, which we are now ready to do. We'll start with a slightly simplified definition. A power series is a series, sum n equals 0 to infinity, of c sub n x to the n, which is c0 plus c1 times x plus c2 times x squared, etc. forever, where x is some variable, and each of the numbers c sub something or other is just a constant. So those are just real numbers. We call them the coefficients of the power series. And before you get too intimidated by that definition, let's take a look at a simple example. Here's one where each of the coefficients is just 1, and so we have the sum n equals 0 to infinity of x to the n, which is 1 plus x squared plus x cubed plus x to the fourth, etc., and on and on and on forever. And the beautiful thing about this particular example is that you have actually seen it before. We wrote it slightly differently, the only real difference being that we used the letter R instead of the letter X, but this power series is the geometric series. Each term is X times the term in front of it. And so by our study of geometric series, we know precisely when this power series converges. It converges if and only if the absolute value of X is less than 1. Other than that, it diverges. And so this demonstrates sort of a typical idea about power series that we'll be paying a lot of attention to. Given a power series, for what values of x does it converge? And for this particular one, it converges precisely for the values of x between -1 and 1, not including the points -1 and 1. Let's look at another example, the sum n equals 1 to infinity of x to the n over n. Here I'm starting at n equals 1 because I don't want to be dividing by 0, which is what would happen if I started at n equals 0. And just for entertainment, the first few terms of this series are listed here. It won't really matter in terms of what we're going to be doing. And what we're going to be doing is trying to determine for what values of x does this power series converge. And our main tool for figuring that out will be the ratio test. The ratio test considers the limit as n goes to infinity of the absolute value of the a sub n plus 1th terms divided by the a sub nth terms. The a sub n plus 1th term in this case is x to the n plus 1 over n plus 1. And the a sub nth term is just x to the n over n. And so applying the ratio test, we look at that limit. The limit as n goes to infinity of the absolute value of the a sub n plus 1th term divided by the a sub nth term, and dividing by x to the n over n is the same thing as multiplying by n over x to the n. And there's sort of the usual simplifying that you can do. X to the n plus 1 is x to the n times x, and so the x to the n's cancel. And that leaves us with this limit here, which we can rewrite as the limit as n goes to infinity of the absolute value of x times the quantity n over n plus 1. Pulling out the absolute value of x is just algebra. The x was in the numerator, so you can think of it as x over 1. And then we can drop the absolute values in the n over n plus 1 term because n is a positive number, and so obviously so is n plus 1. And so that term is all positive. Absolute value of n over n plus 1 is just n over n plus 1. And the next step is the real beauty. It's that as n goes to infinity, what happens to x? Well, nothing at all. X is a constant as far as n is concerned. It doesn't change as n goes to infinity. And the beauty of that is you can pull a constant outside of the limit. And now it's very easy to compute the limit as n approaches infinity of n over n plus 1. That limit is just 1. And so we're left with the absolute value of x. By the ratio test, this power series converges when this limit is less than 1. And so the power series that we're looking at converges whenever the absolute value of x is less than 1 and diverges whenever the absolute value of x is greater than 1. Meaning if you plugged in 3/4 for x into this power series and looked at the sum 3/4 to the n over n, that would be a convergent series. If you plugged in 5 and looked at the sum 5 to the n over n, that would be a divergent series. But we're not done, because there are two situations that the ratio test tells us nothing about. In particular, the ratio test doesn't tell us what happens when this limit is equal to 1. And so when the absolute value of x is equal to 1, we don't know if it converges or diverges. We have to test those situations separately. And if you plug in x equals 1, you get the series sum n equals 1 to infinity of 1 to the n over n. And since 1 to the n is just 1, this is the harmonic series, which we know diverges. On the other hand, if you plug in x equals -1, you get the sum of -1 to the n over n, the alternating harmonic series, which we've seen converges by the alternating series test. And so what we've determined is that the series that we're looking at converges for all values of x between -1 and 1, including the -1, but not including the 1. In interval notation, you write that like this. The square bracket shows that the -1 is included, and the parenthesis shows that the 1 is not included, and it diverges for all other values of x. Okay, I had mentioned that our definition of power series was simplified. Here is the complete definition of power series. The only difference being that instead of x to the n, we now have x minus a to the n, where a is some fixed real number. And so the simplified version that we were looking at, you can imagine that it always had a equals 0. If you said a equals 0, then you get exactly the definition that we were talking about before. This is called the power series centered at the point A. And to see why we call it that, let's look at an example. We'll vary the example we just did, and instead of looking at x to the n over n, we'll look at x minus 5 to the n all over n. And applying the ratio test, we'll look at the limit as n goes to infinity of the absolute value of the n plus 1th term divided by the nth term, and as before, dividing by x minus 5 to the n over n, same thing as multiplying by n over x minus 5 to the n. And also as before, the x minus 5 to the n plus 1 is x minus 5 to the n times x minus 5, and so the x minus 5 to the n's cancel, giving us this expression here. And the rest of the work is also completely analogous to what we just did. X minus 5, or the absolute value of x minus 5, is a constant as far as n is concerned. As n goes to infinity, absolute value of x minus 5 doesn't change. And so we can pull it outside of the limit, and the limit as n goes to infinity of n over n plus 1 is 1. And so we just get absolute value of x minus 5 as our limit that we're computing. The ratio test tells us that the series converges if the absolute value of x minus 5 is less than 1. And that happens when -1 is less than x minus 5 is less than 1. And adding 5 to all three sides of that inequality, we get that this is when 4 is less than x is less than 6. So this series converges for all values of x between 4 and 6. It diverges when x is greater than 6 or less than 4. And just like we did in the last example, we have to see what happens when x is equal to 4 or equal to 6, because the ratio test won't tell us whether it converges or diverges. In those cases, we'd get that the limit is equal to 1. So the ratio test is inconclusive. And so we have to test those two values separately. When x equals 4, 4 minus 5 is -1, and so we get the alternating harmonic series, which we know converges by the alternating series test. And when x equals 6, 6 minus 5 is 1, and so we just get the harmonic series, which we know diverges. And so finally we can conclude that the series that we're looking at converges if and only if x is in the interval from 4 to 6, including the 4, not including the 6. And this justifies why we call this a power series centered at 5. 5 is in the center of this interval from 4 to 6. Okay, we'll call that a pretty good stopping point in our introduction to power series. There's plenty more to know. In our next video, we'll take a closer look at what kinds of intervals a power series might converge on. See you soon.